Okay, thank you very much. Sorry, I'm a little late. Yeah.
That's fine. You can start.
Okay, okay. So the topic today is linear state modeling in mobile health and diagnostic classification. And so here, an outline. So basically, I mean, the mathematical structure is that of hidden Markov models, HMMs, and the computational technique is MCMC methods. And what we are going to focus on is latent state modeling in mobile health. Okay. And I'll review some of the recent literature, and also, I mean, how, this technology can be used for it. Then another problem is, closely related problem, is diagnostic classification models in psychometric testing. And now, so what I want to describe is a new MCMC approach, and actually this work had been developed with, Professor Hoping Chan, who was my former PhD student at Stanford, and then he came back here, and then and actually this new MCMC approach was developed about 10 years ago, was started, okay, I won't say developed, okay, so 10 years ago when he visited me at Stanford during his sabbatical. And now, so after, so today I will be talking about this technology. And then actually in recent years, okay, quite recent, okay, it was probably started last year, when I visited University of Illinois Urbana-Champaign. And actually I visited, actually my whole career was spent at Columbia and Stanford. And I took a leave in 1975, okay, to 76, and visited UIUC, okay. And essentially, and started working with people there. And I mentioned, okay, after so many years, when I pay another visit to UIUC, and then this closely related project, psychometric diagnostic classification, so popped up, and it is related to this, mobile health, okay, or at least the way that we look at it. And so finally, I will talk about, okay, with this particle, what we call adaptive particle. Actually, MCMC state substitutions turn out to solve the problem of adaptive particle filters, which is what I started with Hoping, okay, 10 years ago. Actually solve it very neatly. And so now, of course, we can now use it for mobile health, and I can look at this problem in the broader context of adaptive filtering and control in mobile health. So here is some related work that is connected to this workshop. And here, so I will be talking about which is really the first paper, about a paper by Walter Dempsey, who was a postdoc of Susan Murray, and at Michigan, and when Susan moved to Harvard, Dempsey moved with her. And they published a paper in 2017, and they used continuous time HMMs, okay, hidden Markov models, to model the time to event outcomes. Now, for example, what they were interested in is lapse to alcohol or illicit drug use. So that's the, using these variables, mobiles, okay, they want to predict, okay, the time to event, okay. So here is, essentially, they want to build a risk model. And now what are their data? Okay, what do these, what do these mobile and variables provide? So basically, multimodal is that, it's not just one source of data, it's multiple data streams. So these are the sensor streams. And now, of course, along with self-report. So the person may report or may not report, but there are sensors. So now, how do we? So their problem is really, you have all these sort of fit, okay, the person with this data collecting things, okay, and also ask the person questions, okay. And so what they want to emphasize in this paper is they want, okay, so now actually you collect all this information. So that is, I think they explain this hidden Markov model, very clearly. And also why they use a continuous time Markov model. I will return to this. And here, basically, that's the point, okay, that I want to emphasize is latent state modeling. Because, this person have this, but now at the end of the day, what are you interested in? So you're interested in, okay, you analyze this data, but you sort of have to think of your bottom line. And the bottom line are interpretable states that represent behavioral constructs, such as stress and craving. So illicit drug use. So maybe, somebody craves for that. And now, here, you have these sensors, multimodal data. So the measurements are noisy. And especially not only are noisy, okay, may even be biased because with self-reporting, they may choose not to report. So anyway, you have noisy observations. And you want to relate your noisy observations back to the states. So that is where the hidden Markov model is important. And now here, so at the end of the day, you have now, besides these, state, and there are, how do we quantify, the person's behavior and so on. So you sort of look at them, okay, embed this model with parameters. This hidden Markov model will, okay, now relate the state, and then there are certain, and at the end of the day, your ultimate decision will be guided by these parameters, okay, in the model that capture domain knowledge. So this is, I'll return to this paper, a recent paper at the end of the talk. Now, the one, okay, I talk about UIUC. In fact, the person, when I visited in 1976, actually I visited the probability group, okay, mostly, and that was where Joe Dube and Bill Stout, Walter Phillip, and so on, were there, okay. And so and now afterwards, okay, so I even wrote a couple of papers with Bill, okay, afterwards, they were in probability. But in fact, after I left, okay, on this way I returned to Stanford, Bill spent a sabbatical year in Washington. And now then he got interested in educational testing. And so when he went back to UIUC, after the sabbatical, then later he was basically his research, refocused it on psychometric tests. So of course, and he spent a year, okay, at educational testing service and so on. And also many of his students went there. And here the tests, okay, of course, mean these are multiple choice tests. And now what Bill and his collaborators, okay, at UIUC, DiBello and Hansen, whom I must confess I never met, they replace, so usually in psychometric testing, you score, either the answer is right or wrong, and here is 0, 1, okay. But instead of that typical score, okay, that commonly used, they came up with this idea of polygamous scoring. So actually, the examinee's response, so here so the examinee maybe simple guessing, he doesn't know the answer, so he just bets on which one, so it's G. And then the other, okay, what they really want to find out is if the person gives the wrong answer, okay, dichotomous scoring is wrong, then, okay, now maybe the person doesn't know anything and just guess, okay. The other is, the person does know something, and he wants to give, this a cognitive, they call cognitive response. And here, and now of course at the end, okay, it's wrong, but they may be wrong for different reasons. So here is the option of incorrect or incomplete cognitive thinking, or lack of certain skills from wrong answers using C. So in C, I mean, they further classify. So this is what is called diagnostic classification. So now, so here is this model, okay, that they have been developing, I mean, I think since 2000, or at least Bill Stout and his students, okay, and colleagues. And now, so how do they relate these latent states and also their parameters to, I mean, the ultimate, so how do they do this diagnostic classification? And that is, they use this Bayesian approach, which I'll come back. Okay, so now, so let us put it off for the time being. And I'll explain, I mean, the basic mathematical structure of what we are doing. So first of all, about filtering. So you have a Markov chain with latent or hidden states. So that's the framework. Okay, so very much like what we say, we have latent states. Okay, that reflect certain things we are really interested in, but we do not observe those states. Okay. And so, I mean, I talk about diagnostic testing. Is this person, first, okay, you may be guessing, or actually maybe just, give a cognitive response, okay. And, with the three options that we have talked about. So these are the states. And now what we know, okay, is whether the person gives the right or wrong answer. So the whys are, the answers. And of course, depending on the question, this is actually more complicated. It's not just y is 0 or 1, but it is conditional on this state, okay, depending on how you model this state. So you have the state undergoes the Markovian dynamics, so it only depends on the previous state. And the observation depends on the state, okay. So, PT and GT are density functions respect to some measures. And a pioneering paper is by Gordon, Salmon, and Smith. Okay, Gordon and Salmon are engineers. And, Smith is Adrian Smith, okay. The famous Bayesian, in our community. And they introduced particle filters for estimating the hidden states in HMM. So, that's what they did, okay, and now later, actually, I was lucky in a sense that actually I didn't know any of this work, but Jun Liu, okay, was a colleague, okay, at Stanford, okay, at the time, and he taught courses, he was writing this book, okay, and he taught a course out of this, from which this book was developed. And Jun Liu later, moved, so he actually came from Harvard, okay, and to our department, and later Harvard sort of recruited him back, so he went back to Harvard, and but actually, many of our students learned that stuff, okay. So and it provides a collection of techniques that have been developed up to that time. So as I said, I know absolutely nothing about this subject, but through Jun Liu students, actually one of them, because after Jun Liu went back to Harvard, one of his students, actually who currently is at UIUC, Hugo Chen, came to ask me, to co-direct his thesis. So since I had to be his thesis advisor, so I sort of picked up the material essentially from Hugo Chen. And now, so that's around 2000. Now, and actually, Hokping Chen and I we were not, interested in this, we were not working on this problem, of course. But we were interested in simulating rare events, okay. So we had this research agenda, and actually, it started even in Hokping's thesis, on, fault diagnosis, okay. So it's something, there is this idea of fault detection. But now, after detection, where's the source of the fault? So this is what is called false diagnosis. And now at the end of the day, okay, false are rare, so you have rare event simulation coming in, and also you have to do the diagnosis. So then, I mean, in order to tackle that problem, we rely on simulations, and then we try to figure out a way. And of course, rare event simulation is very, very important sampling. But actually, as you will see, important sampling, I mean, first, it's very hard to find the importance measure. Very hard. I mean, of course, you can do it, but then you can create large variance. So, how do you do it efficiently was the problem that we thought about, and we actually tried to hang close to the optimal importance measure. And actually, this what happened is, okay, the techniques, okay, that I sort of in this other field, hidden Markov model, does help us. So, I mean, now having solved the rare event simulation problem, then we thought we could also solve, I mean, this particle filter problem. So that was, and over the years, okay, we sort of finished that project and developed it, okay. So now here is, so let us now go back to particle filter. And now the particle filter, okay, the way it goes is this. So now you look at x1 dot t, okay, as this, I mean, the whole, I mean, sequence, okay, of outcomes, okay, of states up to time t. And now you are interested, okay, so actually the filtering problem is you are interested, I mean, basically if it's in the Markov, you are interested only in the final state. But actually the way we think about this, and that is what particle comes in. So particle filter is actually thinking of the whole trajectory. So this trajectory, which is a particle, and you try to simulate this. So conditional on this sequence of observations from 1 to t is, I mean, I use this pt tilde. So it is proportional because actually now it is Markov. So I think pt depends on the previous state, xt minus 1. And then, okay, and then at, okay, and then given t, then the yt has its density gtyt, okay, which is, I mean, which is here, okay, notice gtyt, okay, so that's we are just using these two sources of information. So, I mean, and now, of course, I mean, once, because of the Markovian, they're conditionally independent, so you have t, the product t1. So this density is proportional to that, and of course there's a constant of proportionality. And now, so this is really, I mean, up to here, this is very standard, but that is really the Mcmc, okay, is introduced to help it. So this conditional distribution is often difficult to sample from. And because the normalizing constant is difficult to compute for high-dimensional or complicated state spaces. And particle filters use sequential Monte Carlo or SMC that involves important sampling, which is clear, okay. We cannot sample from this, so you do importance. Just like for rare event simulation, that's what we do. And now, but then, okay, actually, if you do important sampling and just let it go, then actually this like ratio will have very high variance, okay, eventually. And so there is this step, okay, and that is the Gordon Salmon Smith, okay, idea is to do resampling. To bring it back. So here, the weights, because you get importance weights, and the weights are too scattered, okay, are not, okay, I mean, in other words, you put a lot of weight, okay, on, put on just a few, okay, a few particles with very large weights, and the other have small weights, then you will run into a problem. So the way to do this is to do a resampling step. So this is, there's this resampling, and then to just bring it back. Okay, so here the conditional, so this is the SMC most important sampling, and so which is actually pretty obvious. But then the clever step is resampling that circumvents this difficulty. So here the way is now how do we do it? It is Monte Carlo. So Monte Carlo means that, you are going to generate a lot of these, okay? Otherwise, and then average them. So the way is we take, okay, that's the sample path of the nth particle. You can think of particle as a trajectory. And then, so here is xt dot t minus 1m, okay, up to time t minus 1. And now you have m particles. So what have this algorithm, you can think of this SMC as an algorithm, computation. It uses importance sampling from a proposal density. Qt is something you choose, and of course you would like to choose it cleverly. But how, okay, we'll talk about it later. To circumvent this difficulty and updates not only the particles, but also the associated weights and ancestor. Now actually, these weights, and the way, okay, because I said, okay, so this is the what people have done, okay. But to us, okay, we are not satisfied with, what people have done, because you see, we started out not really doing particle filter. We started out doing rare event simulation. So if you do rare event simulation, which is simulate probability, you must tell the user the standard error of your simulation. Otherwise, okay, it's not going to be useful. And therefore, so we spent a lot of effort to really analyze that standard error, and we found, okay, the formula, for the standard, this variance, which can be consistently estimated, and actually it relies on what is called the ancestor or the ancestral origin. So that is why we do this, and besides, so the algorithm doesn't, the particle doesn't need, okay, this ancestral origin, but we want to get the variance of the estimator. So we bring in, okay, so this is our major advance is we are able, these things are particle filter are interacting particles, okay, in statistical mechanics, these are called interacting particles. And actually they are very complicated, but then we have been able to resolve that difficulty. So there is initialization step. So here is the algorithm can be simply stated that, two things. Now so we have at say t minus 1, then you have this, at t minus 1, you have, already have the particles. So now how do we update? So the update is first do the resampling. So resampling from, this set of particles and also the ancestral origin, okay, that I keep here. And then I resample, okay, using the, I have the importance weight for each of these particles. So I sort of take, okay, with this sample with this probability. So this is what is called bootstrap resampling. And then, okay, so now I resample to get, this, in other words, to get this. Then, okay, the next step, so this is the resampling step. The next step is to now actually to sample the next, to form the next particle. So, which is to sample this, for the nth particle, you now have to add, update this. Okay, so you need to sample. We know this comes from this proposal density. So that's what it is. And then you update. Okay, so that's the weight update, which is obvious. And then, of course, the particle, you just add this to the previous particle, to the particle up to the trajectory up to t minus 1. And so step 1 of the algorithm is often referred to as bootstrap resampling, while step 2 corresponds to importance sampling. And it yields, the importance weights WTM. So, yes. Okay, so ancestral, I will, at the end, I'll come back to it. Yeah, it doesn't need ancestral. You are right, okay. So here the SMC estimate is pretty clear, right? So I'm just, I have these particles. I want to estimate this, so psi, okay, I want to estimate the expected value. So that's, given the observations, okay. So here I take this, I have the weights, okay. And then you have, you sort of take, okay, the average. So here I am such, and then I average all over the weights. So this is, I mean, so we don't need any ancestral. But the whole point is, I mean, this is why what we have worked that hard on, is that we actually now, under regularity conditions, okay? So there is, so just like, okay, I said my motivation of working on this is really our original is we didn't know anything about particle filter, and we didn't really, but we actually were just using these ideas to do rare event simulation. So, but for rare event simulation, we must be able to tell the user, I mean, what is your standard error? And so, and this is really that, I mean, it actually, we already had that, those calculations done in an earlier paper on rare event simulation. I think that was maybe 2007, published in the Annals of Applied Probability. And then it was after that, okay, then, okay, having solved the problem, okay, then we thought we could actually do particle filter. So it didn't take us too long, okay, so all those calculations do carry over. So, and actually this ancestral origin comes from the martingale representation of, I mean, of course, I mean, the important step, because it's recursive, you see, so it is pretty obvious. But actually the resampling step was, I mean, so we decompose, I mean, this, okay, I mean, this, we represent the estimate, okay, I mean, is unbiased, so your condition the past, that kind of things, okay. And you write this in terms of a martingale difference sequence, okay. After you scale things, okay, you have a sum. And then after that, okay, because basically representing the other step, okay, the resampling step, we got to this ancestral origin. So there is this, I don't think I have put it here. And actually in the paper, 2013, okay, I mean, it is all described, but in fact, to get the motivation, okay, how did we come up with this idea is we are just copying from, okay, our earlier idea, okay, which was really, I mean, essentially, I mean, a martingale representation of, I mean, this, I mean, the important sampling step and the resampling step. So we, okay. And now, so now we go to this, so that was 2000, so we basically completed that work, okay, before Hopkins visited me. So now Hopkins visited me, spent sabbatical at Stanford, and basically also to write up, okay, the previous paper. But, and then here is the problem. And I'll explain how this problem occurred to us. So you have, in practice, hidden Markov model has unknown parameters. That's what we have just said, okay. So you are like, okay, unknown parameters are actually very important in to reflect domain knowledge, like in this, in those two examples I talk about. And so here, the next step is when you do modeling, okay, now what do we do with these parameters? So the naive approach is, since it is a parameter, and you don't know, then you can look at it as a state, and you treat it as a hidden state, and proceed with the usual particle filters, with multiple thetas generated within the same particle filter. However, this causes a problem, because, I mean, you need this resampling step. So repeated resampling because the parameter is static, so if you do repeated resampling, it will result in a few distinct values of theta, and you get degeneracy of these enlarged particles. So, so people actually knew this, okay. So a standard Bayesian approach is to estimate theta by Mcmc and then apply the estimate theta hat to the particle filter. So all this, okay, I mean, people have been talking about. Of course, again, okay, I didn't know anything about that at that moment. But actually, you see the good thing of working with students who have different motivations. So there was a student at Stanford, okay, and actually, so he initially worked with another person, okay, in the management science and engineering department, and then he sort of knew, okay, or his advisor knew that we had done something like this. So his advisor wasn't interested in this problem anyway. So his advisor told him to talk to me, and so he came over, and actually this problem was, in those days, okay, was actually pretty prominent, in the field of financial, modeling, okay, or volatility modeling, okay, in finance, and this is what is called the stochastic volatility model. And so actually so that's nothing, so lots of people were doing that. But the thing is there were a couple of papers, I think in Journal of Finance or Journal of Financial Economics, that came up, and the authors, claimed, to have ways of doing this. Okay, so that was really the background, and it so happened Hopkins was visiting me, so I sort of asked, okay, look at us, Hopkins to look at this problem. And actually what happened is, the citation, okay, what was, okay, actually, in fact came from another group in statistics. So the reason why these finance people at Columbia, actually at Columbia Graduate School of Business were able to do this is that they were implementing something like that was talked about in a JRSSB discussion paper. And there were a series of papers by Andrew, Doscheit, and Hollenstein. And here is, okay, now, they use this, what is called particle MCMC. So essentially, they use MCMC iterations to approximate the distribution. So now, ultimately, it's a joint, the problem is clear, a joint state and, parameter estimation. So that's and now here, the idea is pretty obvious, okay, when we look at it, okay, now because you want you want to do MCMC, okay, just like Bayesian calculation on theta. So you draw it, just like MCMC sample from a proposal density. And now having simulated that, okay, so you have, now is you look at P theta star, okay, and now you have to approximate this density. Okay, because this density is conditional, you don't know the parameter, this density is conditional on the parameter, so you just do SMC. And now the SMC is used, to approximate, to use these M particles to approximate this thing. So, and then this approximating particle filter is used as proposal distribution for Metropolis-Hastings update of this. So that is the idea. And there is a variant, there's a variant, okay, of this, and that I think in the next slide here is, called SMC squared. Okay, so that's the background. And actually, what happened is in the JRSSB paper, and also a subsequent paper in the Annals of Statistics, then the idea, okay, so is that they develop, because it's MCMC, so you need to have a convergence theory of MCMC. So they propose PMC to approximate this distribution, as I said, and then, okay, they sort of show, okay, invoke some sort of theory, to claim, okay, this convergence. So it's the usual Markov chain convergence theory, okay, the convergence stationary distribution. And of course, there are always the way to implement this is that, usually it cannot be automatic. You have to do diagnosis on whether, this has converged or not. If not, keep, okay, iterating. So that's the background. And and that is the flowchart, okay, which of their algorithm. So which I will not. Okay, so that's that's what, okay, what the student came to talk to us, Now the student read the papers, okay, from the finance, and also he also read, okay, these papers, but he didn't quite understand the statistics paper, so he came over and talked to me. And then the whole thing is very hard to implement that scheme. So the student, okay, he developed his own implementation and also tried it. He doesn't know whether it works well or not because it's very hard to just simulate many times, okay? Because you even run one simulation was applying to real data, financial data, and it looked reasonable. But how good it is, okay? And to what extent? So this is where, that problem arose. So I think, so one of the things that we look at, of course, is the following that occurred to us. Is, you see, PMC basically uses likelihood of this parameter for theta computed by SMC to update the posterior. And the computation is expensive and therefore wasteful because metropolis Hastings is basically acceptance rejection sampling. If you reject, okay, then you have to start over again. So, and that is just too wasteful and now to do this. So then, okay, it occurred to us, okay, to approximate the target density distribution, because after all, you have data by a set of n representative atoms, because after all, that is the key idea of, original particle filter, right? That kind of things. Okay, you are just representing the distribution by the particles. So here we can also represent the thing by the, instead of doing more generally, for, so I call it, instead of particles, I call them atoms, because later you will see why. Because particles, okay, for the trajectory, and atoms are just, after all, we want to simulate the posterior distribution of these atoms. So now, instead, so essentially I have capital N representative atoms, and I choose them sequentially by an Mcmc scheme, okay? So that instead of rejection, okay, I'm just deciding, okay, so I have N, okay, I will at most substitute one of them, okay? So actually, and so that it will converge, okay? So that is the beginning of our idea. And then, so the next thing is, we see how it works, okay? We will implement this and see how it works. So this is a set of atoms chosen, and then each Mcmc iteration substitutes. So the different thing from metropolis Hastings is it only has one, okay, a trajectory, okay, one sampling. So we have multiple, okay, we have capital N, and then, okay, and then so that every time we only substitute one, okay. And actually, so we try this, and actually is the algorithm. So here is Mcmc sequential substitution. The updating procedure is this. So now, notice I now no longer think of particles, but later towards the end, near the end, I will combine all of them. So here is a detour, of rethinking about Mcmc, okay. To estimate a parameter. So theta is this parameter, okay, you sample from a proposal density, as a candidate atom. So now you have, so here, you have this data now, a candidate atom. So now the update. Update is you go, so now I'm still at k-1 stage, okay? I haven't got to the k yet. So here is this candidate atom. Then I will now add it to my atom set. So now I have nu plus 1, okay? Atoms, okay? So basically now here the notation is a little, let me go back, slow down a bit. So here, so notice, okay, I say capital N. Actually it turns out, and actually this whole thing later, okay, finally we really understood, okay, it was quite recent, maybe a couple of years ago, what was really happening. And actually we need a large, okay, intuitively we need a large number of atoms, okay. to reflect that. But now you see, so we actually tried it, and it seemed to work. But then it was very hard to prove, because your state space, okay. This, after all, I mean, you talk about Markov chain theory, Markov chain has to live in a state space. And if your state space has growing dimension, then, I mean, there's no theory, okay, of Markov chains, okay, because you have these different chains, okay. So, and that was actually very hard to prove, although that was the first kind of ideas that occurred to us. And that actually seems to work, okay. And we do need a large number. So the way we did, I mean, ultimately is to break this capital N into blocks of size nu, okay. So nu is a fixed size. So now you still have chain, okay. I mean, within each block. So within each block, so this is, I mean, about this slide. So here I am now breaking it into blocks of size nu, okay. So nu is, so the state space is, and now I have, I mean, capital B blocks, okay. And so B times nu is equal to capital N. You can rethink of it this way. So now, so the blocks, okay, will act independently. The substitution only occurs within each block. So that's why there is this notation. B is fixed, and now it goes from nu minus, k minus 1 to k. So you sample the atom, okay, as a candidate atom. And now, so here, I will decide whether, okay, so I enlarge my atom set. And of course, by the end, okay, I will have to shrink it back to nu, size nu, okay. Otherwise, I will increase the state space size. So I compute this, the Likert ratio, okay. So here, you have Q and versus the target density, and basically, just like Metropolis Hastings, you assume you know the target density up to a normalizing constant. So that's the standard, okay. But now here is, I mean, the way, okay, we do is a modification of Metropolis. Metropolis is, I mean, I look at this Likert ratio, then I do other things to decide, I mean, whether I do a stochastic, I mean, kind, okay, Markov chain, okay, so that I get a reversible chain, that kind of, so for example, I mean, operation on this Likert ratio and see whether I accept or not. Here, I mean, actually it's very different. What I do is that I have now in this enlarged set. So now I look at these, I mean, Likert ratio, so this Likert ratio, okay. So each one, okay, has this Likert ratio. So I take this average, look at them, okay, sum them, okay. So these will be the probability. Use this, and now I sample this from that, and now, okay, if it is the next, if I have sampled out, okay, from this new plus, actually is the last one, the added set, then I don't change, I don't do anything, okay. So this added set, okay, is basically is not substituted. On the other hand, okay, now, okay, this added set will, okay, in other words, okay, this probability, okay, will be, okay, so I will include it, okay, in this v minus 1, and I will remove, okay, I mean, the jth one, okay, in other words. So the idea is, you see, if you look at this, the reason why I do it this way is if this Likert ratio is big, that means they are different, okay, more different. So I would like to use things that are more, so in a sense, you see, implicitly, we want this, what we want to choose, okay, I think this is the idea of importance sampling that we have played along. I want the importance density to be as close to, I mean, the target density as possible. So that is basically, I basically implement this through sampling. Okay, so here, so that's what I mean. B disjoint sets, theta B0, so that is the initial thing. So essentially, I have a fixed state space, okay. So theta to the power nu, okay, you can think of this way. And then we use to update this atom. Okay, so here is this procedure. And then what happens is, So I would state the results, and then I'll later say how do we get this result. So we can now, basically, we have a central limit. So essentially, the estimate is pretty clear. I'll take the average. I will for each block, and I will average over the blocks. And now there's this kappa is the burn-in period, because the Markov chain needs some time for burn-in. And then, so that's this thing. And then the variance estimate is really very simple. The variance is essentially, treating them as independent particles. Now, why? Okay, that is really the next thing. So here, the main theorem, okay, I'll get back to this. So if your target, so this assumption C says this target density, this likelihood ratio. Okay, now of course you have this gamma. Okay, you are sampling from a proposal density, a family of proposal densities, and I want to choose the one that is as close as possible. So that is this N, capital N. You could do that, and now so basically. Essentially, this whole thing behaves like independent. Now, and actually the challenge is why, okay, so which I will postpone later. And now, so here, so once we have got this, then there is a choice of this proposal density, okay, so it's from this family. And how do I choose Q gamma to, now, I say originally there's an assumption. In other words, I'm able to find such family to satisfy this. But how? Okay, how? So here is this choice of this family. So actually what happens is, in practice, your target, if, for example, I know my target distribution is normal, Gaussian, for example, so you have a mean and variance, mean vector and covariance matrix. So now, okay, so this is really, I just use an example. And now, so I know, okay, this is Gaussian, and so these proposal families are Gaussian, density are Gaussian, and then so you have this. And now here is, and now what happens is, if this family of proposal density, Gaussian densities over on this parameter set, actually is smooth in a sense, actually, sorry, okay, in fact, let's take a new V, I haven't defined V yet, okay, sorry, I've used an old slide. So now currently, let me assume V equal to 1, okay. And in fact, later I extend this, okay, probably I will, I didn't change this slide, okay, but let us take nu to be 1, okay, for the time, V to be 1 for the time being, then C satisfied. So now once we have, so if, in other words, if your proposal density, if this target density is in this family, then actually this scheme essentially will be choosing the, because we are doing substitution, okay, we are trying to find, okay, the way, okay, we'll be finding this gamma. So now, but also you have to tell me how you find this gamma. So in this case, we define gamma B k minus 1 to be the average of these, okay, in this atom set, and involve transitions, the B block up to this, and for k less than kappa, before the burn-in period. And on the other hand, okay, now, because so far I'm just doing for block by block, okay, nothing very exciting going on. On the other hand, after the burn-in period, we can pull across blocks and estimate this consistently, and use it as this modifier for all the blocks. So, and here there's this oracle property, since, so we're probably approaching 1, okay. The candidate atom, okay, substitute some, so essentially, I'm just, and for large K, okay, the conditional density of this given behaves like the new-fold product density, and so on. So, and this limiting. So here is the explanation. Okay, the reason why. Okay, we have those is that we sort of substitution scheme, and the way we choose these parameters. Essentially try to make it work that. And now, what if this rho? What if my proposal density I say is Gaussian, for example? But what is my actual density is not in this framework. So now there is still, basically, I mean, we are essentially choosing the one with this, I mean, the one that is closest, okay. This, we are choosing the way we do, choosing this gamma that is closest, I mean, to this proposal density. So this is in the smallest Kullback-Leibler divergence, okay. Between, okay, these family of measures, and in which case, okay, our estimate will be 1 corresponds to 1 doing important sampling. Okay, so so maybe let me see if I have that slide. So unfortunately, and let me go further down. Okay. Okay, I didn't. Okay, so let me. So here I didn't. So I messed up with these slides. So maybe I'll just explain a little bit why, how did I come up with these kind of things. So there's no V, okay. So V is, I say V equal to 1 for the time being. V is later added. So the way, okay, the calculation we did, notice we don't have that much to work with. You see, we are just doing a substitution. So the way is to analyze, okay, the Markov operator, I mean, associated, I mean, with this. I mean, so the analysis of convergence and so on is somewhat different from what people usually do, like use Harris recurrence and that kind of things, okay, and also couple. But then, but actually, on the other hand, it is very close, okay, because actually my next door neighbor is Percy Diaconis, I mean, who has been doing these kind of things, okay, I mean, over the years with card shuffling. So here I do MCMC state substitution, okay, is an MCMC scheme. For him, okay, what has been doing is card shuffling, okay, shuffling cards, okay, that is his, okay, MCMC, that is his Markov chain, okay. Markov chain. So card shuffling. So when in the analysis of the card shuffling scheme, so he basically, I mean, there is, the operation is clear. And so what he basically was doing, have been doing, okay, although, over the years, I mean, if you look at his work, then he talks about, it's basically about that operator. Okay, associated, Markov operator associated with card shuffling. And then if you know his works, okay, then it is very much related to the second largest eigenvalue, okay, of that Markov operator. And actually in this case, okay, what we are doing, and then where does this second largest eigenvalue come in? Because it was basically doing a difference, computing the total variation norm of these, of his works, of this Markov operator, I mean, the measure induced by this Markov operator, and I mean, the uniform, okay, in card shuffling, you want it to be uniform, right? I mean, at the end. So, so how many, so he was calculating the total variation norm, get bounds on the total variation norm. So then, you know, his work, I mean, tells you how many shuffles you need to make it approximately uniform. So in my case, okay, here, it turns out that the Markov operator associated with this operation is also analyzable, okay. So we actually have, and Hockping and I, okay, sort of worked out, okay, bounds, okay. In fact, the very first approach was essentially doing that, but we couldn't really get a rigorous proof because state space keep changing. So now, once we do this, okay, so that proof sort of went through. And now here, and in fact, that's the other thing why I introduce, I mess up these slides, because when we have total variation norm, I mean, that the convergence means, okay, I have a bound. And the bound, I mean, on that means that it is uniform. It doesn't depend on your starting state. But of course, if you have a uniform, suppose I talk about a uniform distribution, okay. Then your starting state is important because I said at the tail of this normal distribution, then I don't expect, the convergence rate will be the same as I said in the middle. So people in Markov chain theory on general states have looked at this. This is what is called V-uniform ergodicity. So in other words, instead of a very total variation norm, okay, we can extend it to a weighted total variation norm. And this is where this V comes in. So, but that is a technical issue. So to make a long story short, our technique is essentially, our technique is basically doing, okay. So now, here is, so how do I use this? So notice, we started out basically trying to do, we started out trying to do, particle, instead of do a modification of particle MCMC. So the original particle MCMC algorithm, as you, maybe I'll go to the easier one, adapted, okay. So the original particle MCMC algorithm is essentially, you do Metropolis Hastings, and basically, the key to it is you use the particle to approximate SMC, to approximate this denominator when you do this Metropolis Hastings step. But but now actually, so that was in our initial attempt. We just follow this, but instead of doing Metropolis Hastings, we use R. But actually later we find, okay, that our theorem, okay, because that is proved, quite generally, because we never commit to what, okay, we never commit to what this, we never commit to what the, so here, so we have this block, okay, and actually you see, we never commit, in our theorem, we never commit to what theta is. So theta is in some parameter space, okay. So originally we thought theta is a parameter, that's how. But theta can also be, okay, because after all you want to find an atom set, okay, or a set, okay, whose empirical measure approximates that of this target density. So here, what we have is drawn state, parameter, and state estimation. So this parameter is gamma, state is x, okay. So why don't we just take this together? Because we actually, the x is, okay, so we want to approximate the posterior distribution of xk, or respectively gamma k, through the empirical measure of, now here for xk, we use m particles, okay. So that's the particle algorithm when you know theta. And then if you don't know, when you know the parameter you don't know, then these are the atoms. So in algorithm 2, okay, algorithm 2 actually can be applied, okay, because of our general state space, okay, we can apply it to this general thing. So the basic idea is to first, now of course, related approximate the posterior distribution of gamma p in the sense, okay, of this, or of gamma tilde p that minimizes the Kalberg-Leibler information, the divergence, okay, and then use this posterior distribution to generate the particles. And actually the reason why, okay, it still works is the proof of the main theorem, okay, of algorithm 2 uses exponential bounds for the total variation norm of the difference between the empirical measure and the target measure under condition C. So as long as we have condition C, so this kind of thing. So we can relax C to accommodate the case when the exponential convergence rate depends on the starting value by using a weighted total variation norm. Okay, as in V uniform ergodicity that generalizes uniform ergodicity in the theory of Markov chain. So I think, okay, so now here is, we can apply it to different problems, okay. And actually, for this, because time is running up, so I have started talking about the work of Professor Murphy, okay, in 2017, okay, and this postdoc Dempsey, Walter Dempsey, and actually their procedure is to model the time to event, for example time, via a Cox model with time varying covariance 6t for the hazard function as mentioned in the third slide, and they call it I survive. And it consists of, here, So first of all, this latent state, because they're different, okay, when I talk about for drug, okay, I mean, there's this craving, okay, and when using illicit drugs, something, okay, is one in what they mentioned, and also the mood kind of other things, okay. So that's these are the latent states. So at the end of the day, you want the person's condition, okay, that so here, these are the covariates in this Cox model, okay. In other words, the time to event, time they are going to use, okay, these drugs. And then they also explain, okay, they have multimodal observation process, okay. So this J labeling the data stream, okay, these are where does it come from, okay. So, and this multimodal observation process is related to this XT via this generalized linear model, okay. And then this, because these are discrete states depending on different, so these are the Markov jump process dynamics related to this. So the modified parameters are those for the Cox model and the generalized linear model. Then on Tuesday, we heard a talk by Professor Tze Leung Lai, and he gave a review of the accelerometer data and activity recognition. So basically, it's a classification, the resting, walking, etc., from these data in various projects at Johns Hopkins. In which that he's involved. So he talked about, of course, there's a lot of machine learning ideas, classification that he was doing, okay, like here. But now since the activity states are latent, so HMMs have also been used for dynamic diagnostic classification with uncertainty. So here, why this Bayesian kind is you're now on top of this, you can also argue how uncertain you are. So these are some references. And in fact, I think about this, So this work that I mentioned, I have started doing with Bill Stout for psychometric testing, has this flavor. So they develop, okay, this generalized diagnostic classification model, and there's a so Bill and his colleagues have been working on a far-reaching generalization or integration. So the motivation in psychometric testing is there's this item response theory, and also the restricted latent class analysis. So there are two approaches, and they want to integrate, and on top of it, it involves a Q matrix. Now the Q matrix is different from the Q matrix that when I talk about a jump process Q matrix, it is the Q matrix that they use. It is, you have one row per item for each response operation, and it uses a Bayesian approach to model the examinee's latent states. So because there's this classification, which it has implemented using a Metropolis Hastings within Gibbs sampling algorithm. And so due to the large computational resources needed, NVIDIA, has agreed to provide UIUC's project with GPU, okay, hardware, and also software assistance. So NVIDIA is the one, okay, that develops this GPU, and actually his boss, Wang, okay, graduated from Stanford, okay, had a master's degree, and donated now, okay, we have our engineering building is named the Huang Building, okay, which is basically donated by NVIDIA. So hoping to use computational power to solve these problems. So the automatic MCMC procedure, so this is how sort of built, okay, talk to me, and actually ask, because he knows, so because NVIDIA, it is basically through NVIDIA that he approached me. So we found that, okay, we can implement those. And also finally is this mobile cloud, okay, telemedicine. So that's this group is from computer science at SUNY, okay, Binghamton, SUNY State University of New York, and actually earlier this is quoted from their 2017 paper, but they have been this group, okay, have been working, okay, already in 2013, 2015. So they say mobile devices, due to their limited, now here, we have seen in this conference, okay, a lot of good things, okay. But actually, from an engineering point of view, now there is, certain issues. So due to their limited storage space and computational capability, might not be able to perform tasks which require intensive computing and extensive storage resources. On the other hand, cloud computing, because of its unique features like elasticity and scalability in both computation ability and storage space, can be combined with mobile computing to provide ubiquitous and personalized healthcare to patients. And so now they have actually been developing things along this line, and actually this paper that I cited from, and this is the introductory paragraph, and then they actually say, now here you are going to do, combine this mobile computing and, okay, the cloud. So how do you, so there is this scheduling, okay. So I talk about adaptive, in adaptive control, filtering control. So this is a control problem. So they look at dynamic scheduling approach that uses HMM to optimize synergistically the multiple cloud, this mobile cloud-based telemedicine applications. They give one on ECG monitoring toward multiple objectives. So the objectives they mention now, the criterion, is actually a multi-objective optimization problem. You want high accuracy, okay, and you want low latency. Latency means the waiting time, okay, it takes a long time to compute this and give the advice. That's not going to be useful. And also the battery, because you rely on the cloud, okay, then, there's long, the battery life. So that's some current development. So, okay, sorry. Thank you for your attention. So again, I say I went over things very fast because of lack of time, but things will be posted. And probably I'll post a more updated version because I just finished the slides last night. So. Yeah. Yeah. No, I think definitely, because once you have this computation power, right? Because then you can now use, this is what even, I think, the slide I talk about, educational testing, right? That was built because, somebody donates, right? Media donates that computational. So now he can really, of course he may not, okay, ultimately, since I'm new to this, I don't know how useful it is. But actually, at least his field that accepts this to be good, because you just don't score people 0, 1, right or wrong, because somebody makes wrong. But they may know the subject, they may have certain misguided, okay. So I think that kind of things, right? Because you can now, once you have you resolve your computation, right? Then you can do lots of things, right? And also, not only that, you can even connect, right, the data, right? So now there is this technology, people talk about blockchains, right? So now if the regulators, okay, or the decision makers, right, can get your input in real time, right? And also, with the blockchain, you cannot just modify them, right? They have the track record of all this. So all of these, I think what I say is technology is there, already. And how do we harness this technology? And now, of course, also this morning we had, breakfast is not easy because, the companies have a lot of interest in this. They want to, they want to monetize this. They just don't want. But I guess on the other hand, no matter what, right? We can, if you don't, the policy makers, right, also are well funded, right? So all they need is just, have some sort of technology, right, for them, and yeah. And they can also regulate the companies, right? The company. So yeah. So we can have the break, and then I'll be around. So we can chat during break, yeah. So that we don't delay the next week.